Well, previous lesson we discussed about numerical methods for solving initial value problems for ordinary differential equations. The general problem statement is written here. We have a differential equation y prime equals to f of x, y, and we have initial condition y of a equals to y0, and we are going to find solution to this problem. The actual solution is some unknown continuous function y of x. In our case, we are going to find such table of values: x0, x1, and so on, xn, and the values of y, y0, y1, and so on, yn. Here, the points x, xi are known. We have some step that corresponds to the difference between these points, and the values of y, these values we are going to find. We consider different approaches how to find this value, and one of the most simple and at the same time the most maybe the most not the most powerful, but the approach that allows to show the most features of this problem is Euler's method. Here on the slide you may see the formula that helps us to compute the value of a known function y of xi plus h if we know the value of a function y of x I plus h times f of xi yi. We can apply this formula several times and compute the approximate values of y of x I in several points. I show you several examples on previous lesson how we can compute several points numerically using pen and paper. But on this lesson, I want to show you how we can implement this method on computer using C++ in Visual Studio. Well, this program contains several functions. F of x and y is the function that corresponds to the right-hand side of a system of equations. Let's start our consideration from the simplest case. F of xy equals to y. So let's consider the equation y prime equals to y. In this case, the right-hand side is just y. Well, these functions are not necessary now. Well, the next that I must fix here is their initial value, y0. Suppose that y0, y at the point x0 equals 2 and x0 equals to 1. This is a problem statement. What is the exact solution to this problem? It's very simple to find the exact solution. As far as that we know that y prime equals to y, in this case, the general solution will be some constant times e power x. The first derivative of e power x equals to e power x, and the first derivative of the c, some constant, times e power x equals to c power x. And if we know this initial condition, we can substitute this condition here and find that sorry, let's take x0, not 1, but 0. Just for simplicity. If we take x0 equals to 0, then we have this equation from which we can find the coefficient c. 2 equals to c times e power 0. E power 0 equals to 0. Then from this condition, we can find that c equals 2, and the exact solution to this problem is y equals to 2 times e power x. This is the exact solution. So let's declare the function exact. Let's declare the function exact. That corresponds to the exact solution. Well, these two functions describes the problem. We have here the right-hand side of the equation and the exact solution that we can find according to this initial condition. Now let's try to implement the Euler's method in main. What we should declare, what variables we must declare in this case. As far as we are going to find this table of values, first we should declare the size of this table, the number of columns. Let it be size. Size equals to 100. After that, we should compute the distance between two neighbor points, distance between x1 and x0. As far as we consider the interval from from 0 to 1, the length of the interval is 1, and the size is 100. So the distance between two neighbor points is 1 over size. Okay. After that, we should declare the initial conditions. y0 equals 2, x0 equals to 0. This is the initial conditions that we take from the problem statement. What we should do next? As you see in this to apply this formula, it requires to know only two values. Only two values. Values y0, sorry, yi and xi. And using these values, we can compute y I plus 1. Y at the point xi plus 1. So it's enough to declare just two numbers, yi and xi, with initial values y0 and x0. And after that, it's just a message to the screen that we are going to print the values xi, yi at the point xi, and the error. And in this loop, I output to the screen the values of x, the value of y, the value of exact solution, exact at the point xi, and the error. Let me remind you that error is a difference between the real value and the, sorry, the not real, approximated value and the exact solution. After that, I can recompute the values of yi and xi. Xi is very simple, is just previous value plus h. Yi, I should compute using this formula. yi plus 1 equals to yi plus h f of xi yi. So new value of yi equals to yi plus h times f of xi yi. This implementation strictly corresponds to the formula. And that's all. So the solution to this problem can be implemented only in this one loop. Let's take the number of steps, just 10 numbers. And let's run the program. We will see on the screen the table of values. We will see on the screen the table of values. The first value, the first approximated value approximates the real value exactly. The error is 0. And starting from the first point, this approximation will be not exact. And the error of approximation becomes larger, 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 and larger. The final error is 0.25 approximately. If I decrease the step, or in other words, increase the size, increase the number of columns in the table, compute 100 points, the error becomes 10 times smaller. If I compute 1000 points, not 100, but 1000, the error becomes 10 times smaller too. It means that the Euler's method is a first order method. I increase the number of steps 10 times, and the error decreases 10 times too. Well, this is a very simple implementation of the Euler's method. Well, if you don't have any questions, let's come back to the presentation. Let's come back to the presentation, and let's discuss about more powerful methods, so-called second-order Runge-Kutta methods. We begin our consideration from the Taylor series. This is a Taylor series written for y at the point x plus h. From the differential equation, we have that the first derivative equals to f of xy, and the second derivative equals to f of f prime x plus f prime y prime x, according to the rules of differentiation of a complex function. Here subscripts denote the partial derivatives. But the first three terms in the Taylor series now can be rewritten as follows: y x plus h equals to y of x plus h times f plus h squared over 2 f prime x plus f prime y times f, plus the terms that have the error of order h power 3. If I rearrange these terms, I can write it as follows, like it's written here. We are able to eliminate the partial derivatives with the aid of the first few terms in the Taylor series in two variables. We can consider f of x plus h, the first parameter, the first argument, y plus hf as f of xy plus f prime x plus h f prime y, y prime x. And if we apply it, the Taylor series can be rewritten in this form. Hence, the formula for advancing the solution can be written as follows. This formula can be used repeatedly to advance the solution one step at a time. It's called a second-order Runge-Kutta method, and it's also known as a Heinz method. But usually we use the term second-order Runge-Kutta method. How we can apply this formula and how it corresponds to the Euler's method. To explain it, let me write on a board some formulas. First, I switch to the video. I stop sharing the screen. I switch to the video, but I send it you this presentation, and you may open this presentation at every moment. Let me write differential equation first. Problem statement. Y prime equals to f of xy. This is the differential equation. Next, let me write the formula for the Euler's method. yi plus 1 equals to yi plus h times f of xi yi. If we know the initial point, y0 equals to y of x0 equals to y0, we can apply this formula and step by step find the solution. Now, let me write on the second board the formula for the second order Runge-Kutta method. It can be written as follows. yi plus 1 equals to yi plus this part, or even I can write it plus h times, so this plus this part of the formula exactly corresponds to the Euler's method. But the next is 1/2 times f of xi yi plus f of xi plus h yi plus h times f of xi yi. This formula is written in your presentations, in the presentation that I sent for your class. And if you look to this formula, you can see that this value corresponds to the value that we compute using Euler's method. So the second order Runge-Kutta method is so-called two-stage method. First stage, we must find their intermediate value that we denoted with y this line, or even very often it's denoted just as a k. Let's denote it k equals to yi plus h times f of xi yi. This is the first step. I compute some intermediate value k. And the second step, y I plus 1 can be computed as the yi plus h over 2 f of xi yi plus f of xi plus h. So first I compute this precision k, and after that I substitute it here. And this method is 10 times more powerful than Euler's method. What does it? It means that this method has the error 10 times smaller. It's second order method. Second order method. Let's consider how it works. Let's consider how it works. What we should do to implement the second order method in the form of C++ program. Again, let me share my screen. I come back to the presentation and to the Visual Studio. So this implementation corresponds to the Euler method. Okay. Or even this is Euler method. And now, after that, let's implement and output the value for the second order method. Let's reassign the initial values to the same numbers. Y0 equals 2, x0 equals to 0. What we should do first? First, we should compute this coefficient k that I denote in the problem. The first step, we compute k, and to compute it, we use the formula from the Euler's method. Very simple. Second step, we compute yi. We can recompute yi plus h over 2, exactly that I write on a board, times first term f of xi plus the second term f of xi plus h and k. As you see, the implementation is not much harder than for Euler's method. We should just introduce a new step, some intermediate step, and use this result to compute the value of yi. Well, after that, we should update the value of xi and continue the computations. Well, let's compare the results. Let me set size equals to 10, and let me run these two methods. And let's compare the results. First table corresponds to the Euler's method. And we see that the error of computations becomes larger, 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 and the error at the final point is approximately 0.25. But what will we see for second order method? The error of computations also becomes larger, larger, and larger. But you see that at the final point, this error is much smaller than the error of Euler's method. Much smaller. 0.008. Let's compare it for 100 points. And let's set precision equals to 5. 100 points. Or it's not enough. It's better to set it as 8 or 6. No, it's not enough to let it be 8. Or I'm sorry, I set precision only for the first method, but here I should repeat it. 6 and 6, of course. Well, let's compare the results. So, as you remember, the last column corresponds to the error. And the last point, at the last point, we see error 10 times smaller than in the first case, but it still be large. Approximately 0.027 for the Euler's method. But for the second order method, you see that the error is significantly smaller. It's approximately 100 times smaller. It means that this method is a second order method. We decrease the step 10 times, the error decreases 100 times. This is one of the second order methods. But in general, there is a so-called family of second order Runge-Kutta methods. We can write a formula in the following form, where W1, W2, alpha, and beta are parameters at our disposal. If we compare this formula and the initial terms of the Taylor series, we can find that these conditions should be true if the formulas star and 2 stars must be the same. It means that W1 plus W2 equals to 1, W2 alpha equals to 1 over 2, W2 beta equals to 1/2. So one of the solutions to this system is 0.5 for the first two parameters and 1 for the second two parameters. And this set of parameters corresponds to the Hens method. By the way, as far as we have 3 conditions of 4 unknowns, there are infinitely many number of solutions to this system. But from the computational point of view, good solutions are, we have just 2 solutions. This is one of the solutions. And the second solution that is very good from the computational point of view is as follows. W1 equals to 0, W2 equals to 1, alpha and beta equals to 0.5. The resultant method is called modified Euler's method. The formula presented here. Let me write this formula on a board again and discuss about some features of implementation. I close the screen so I can write the formula of modified Euler's method on the board. Y I plus 1 equals to y I plus 8 times. So the first part of the formula is the same. The difference is further. F of xi plus h/2 at the point xi plus half of the step. Yi plus h/2 times f of xi yi. Well, if we look to this formula, we can see that method is also contains 2 stages, 2 steps. The first step, we should compute again the value k, but we should use another formula. Yi plus h/2 times f of xi yi. And after that, we should use this value in this large formula. The second step, y I plus 1 equals to yi plus h times f of xi plus h/2 and k. So this method is also 2-step method. First step, we compute k. Second step, we compute the point yi plus 1 using k. Again, let's look to implementation. Let's consider the implementation. Let's come back to the Visual Studio. Well, now the coefficient k is computed as yi plus h over 2 times f of xi yi. And new value of y is computed as yi plus h times f of xi plus h over 2 and k. That's all. 2 steps. First step, we compute k. Second step, we use k in this formula. Let's check this method. Oh, it's 100 values. Let's write for 10 numbers. This is the Euler method. The error is 0.25. And for second order method, the error is approximately 100 times smaller. If I decrease the step, if it means that I increase the number of steps, the error becomes 100 times smaller. Very powerful method. Very powerful method. Well, I show you just as example even more powerful method that called fourth order Runge-Kutta method. This is a classic formula, and this formula contains 4 steps. During these steps, we should compute the values f1, f2, f3, f4, and each of them is computed using the previous value. To compute f2, we use the value of f1. To compute f3, we use the value of f2. To compute f4, we use the value of f3. And after that, we use all of these values in one formula to compute xi plus 1. This method is the fourth order method. It means that if you decrease the step 10 times, the error will decrease 10,000 times. Very, very powerful method. Well, do you have any questions about second order Runge-Kutta methods? According to our timetable, the next lesson will be the last lesson. And on the next lesson, we will consider how to solve systems of systems of ordinary differential equations. We consider how to solve the high-order differential equations and the systems of ordinary differential equations. And we consider some simple example. We take this example from the very beginning and we solve it. We find the position of the pendulum using the methods for solving second order differential equations. Well, Do you have any questions? Well, if you don't